Добрый день, уважаемые слушатели. На прошлых занятиях мы с вами прошли построение политермических и изотермических разрезов с помощью программы Термокалк, подробно их разобрали, прослушали некоторые видеоуроки по построению разрезов. И на этом видео и в следующих занятиях мы также продолжим. Будем знакомиться с принципом работы термокалк. И сегодня первое обучающее видео, одно из первых видео, это видео по построению или по моделированию однофазное диффузионное моделирование.
This video will show you how to make a single-phase diffusion simulation using the graphical mode version of the diffusion module, also known as DICTRA. This single-phase example simulates the homogenization of a gradient composition of iron and nickel at an isothermal temperature of 1400 Kelvin in a planar domain. At this temperature, the material is fully austenitic, meaning that the only phase present is the FCC face-centered cubic phase. In thermocalc, this phase is written as FCC_A1. The calculation is based on Diffusion Module Example 1, which can now be accessed from within thermocalc in the Help menu, Open Examples, Diffusion Module DICTRA. If you want to run the example as it is, double-click on the example file, then right-click on the top node, and select Perform Now. In this video, I'll walk you step by step through how to set up the calculation and explain what I'm doing. You can learn more about single-phase simulations by going to our online help system. The program opens in an internet browser, but the files are stored locally on your computer, so you do not need an internet connection to use it. From the main menu, go to Diffusion Module, Graphical Mode Quick Start Guide, Single-Phase Simulations. Here you can learn about the theory behind the calculation and more. To begin the calculation, click on the Diffusion Module template from the home screen of thermocalc. All the nodes we need to run a diffusion simulation will appear in the project pane. Highlight the system definer, then select the Demo, Steels and Fe Alloys database package. This will load both the thermodynamic and mobility databases. Select the elements iron and nickel. Select the Diffusion Calculator node, which opens the Diffusion module. Every diffusion simulation requires the user to define 3 items: the geometry, the region, and the thermal profile of the system. If you click on the Options tab, you will see that there are many other options you can define. This is also where you can change the default settings. These options are generally only required with more complex diffusion simulations, so they are placed on a separate tab to make the module easier to use. Back on the Conditions tab, we will set the geometry first. DICTRA is a 1D code, so it is suited for diffusion problems where composition varies along one spatial coordinate, represented in the image by the arrow. The geometry of your system can be planar, spherical, or cylindrical. A planar geometry corresponds to an infinitely wide plane of a certain thickness. A spherical geometry corresponds to a sphere with a certain radius. And a cylindrical geometry corresponds to an infinitely long cylinder of a certain radius. In this example, we will select planar. Next, we will define the region. All diffusion simulations require at least one region to be defined. A region is a named container that designates a certain part of the domain. In this case, because we are doing a single-phase simulation, the one region makes up the whole domain. The name of the region is arbitrary and specified by the user. I will name this one Austenite. Notice that the tab is updated with the name. You can also double-click on the tab to change the name there. Next, we will set the width of the region to 1e to the -4. Notice that when we enter a width, a visual representation of our region appears. Since this is a single-phase simulation, there is only one color representing the one region. If we were to add another region, another color would appear. However, we only need the one region, so I will delete the second. We will accept the default points as 50 and the default type as linear, and we will set the phase to FCC-A1, which is how we write FCC, or face-centered cubic, in thermocalc. Next, we need to set the composition profile, so click Edit. The initial composition profile must be specified for all regions. Since we only have one region, we only need to specify it once. Since our system only has two components, iron and nickel, we only need to set the initial composition profile for one of them because the other will be dependent. We are looking for the composition profile of nickel, so we will leave iron as the dependent component, which allows us to work with nickel. There are many ways to specify the composition profile, and in this example, we will accept the default, linear. Set the profile from 10 to 50. These settings mean that the profile goes from 10 mass% nickel at the left side to 50 mass% nickel at the right side in a linear progression across the width of the region, because we selected linear. This will be shown later when we plot the calculation. Click Apply. Finally, we need to define the thermal profile. We will leave isothermal selected, meaning that it will have one temperature for the entire simulation time. The temperature is 1400 Kelvin and the simulation time is 30 hours. Now click on the plot renderer node. All of the fields have been filled in with information we already set. We want to see how the composition profile has changed from the beginning of the simulation, so we need to add a starting time in the time field. Set your cursor before the 30 and add 0.0, then a space. Now click Perform at the bottom center of the program. Once the simulation is finished running, a plot will appear in the results pane. The plot shows the composition profile of nickel with an initial time, 0 hours, represented in blue, and the final time, 30 hours, or 108,000 seconds, represented in red. If you hover your mouse over either of the lines at any point, you will see the distance, followed by the mass% nickel. We can see that the initial linear composition profile has started to level out. Running the simulation even further would eventually give the same composition in the entire region. We can see this if we add a calculation time of 300 hours. Click on the Diffusion Calculator node and change the time to 300 hours. Click on the Plot Renderer node and set your cursor before 300 in the time field and add 0, space, 30, space. Right-click on the Plot Renderer node and select Perform Now. The plot now shows a third line, representing 300 hours or 1,080,000 seconds. The line is nearly flat, showing that the composition is nearly the same in the entire region. Users can easily save projects to return to them later or share them with others by clicking the Save icon in the upper left-hand corner of the program. If you save a calculation, it can be useful to rename the nodes as a way to help you remember what the calculation is. To do this, right-click on any of the nodes and select Rename. I'll rename this project Diffusion, Single, Phase. When you rename a node, associated tabs are also updated. We hope you enjoy using the graphical mode version of the diffusion module, Dictra. You can watch additional videos about the diffusion module or other types of calculations by clicking the links currently on your screen.
Спасибо за внимание. На следующем занятии мы будем смотреть следующее видео, знакомиться.